Hi, I'm Luke Horn. This is my honors project for Chemistry 1100, General Chemistry. Um, the topic I've decided to do for my honors project is the wave-particle duality theory. This was a topic that we discussed within our chemistry lecture a little over halfway through the semester, if I remember correctly. Let's get started though. So, a wave particle, what is that? Like, what does this even mean? There's a lot to unpack, obviously, but we're only going to open the essentials for right now. So, this is a theory. It basically came to light because we were experimenting and we were observing the patterns of light that we all know, and we started to realize that not all of it could be understood with our traditional understanding of physics and chemistry. Uh, this would be your Newtonian physics. Um, it conflicted with it, but it matched it in some other aspects. We could still predict the behavior of things using our traditional math and physics, but there was something that wasn't getting explained. It was getting lost in translation almost. So, the wave particle theory itself is the idea that light does not follow it, uh, our traditional understanding completely. This has allowed us to find that while it does act as a particle, which is what we traditionally thought, we thought light acted as a particle. Um, it also travels as a wave, giving it a unique presentation, and why we couldn't completely predict the behavior of light. So, I mean, where how does this affect us in real life? And honestly, most of the time it won't affect you. It won't ever. But here's an example: the sun. It's a pretty good example. We all know about the sun. We all know the sun emits light and it gives heat off and everything, and that's a very good basis to explain how this theory works. So the sun's light, you know, it reaches Earth, and this is we it reaches Earth by something we call photons, right? And these photons, my slide says masses, but it's meant to be massless balls or particles of energy that disperse when it's introduced to mass. The mass absorbs all of this energy and becomes a little more excited, increases in temperature, um, and it dissipates, right? The photon no longer exists. It is completely within the massed particle. Um, so these photons, we treat it as a little ball, as a particle basically, but they travel in wavy patterns, like you would see in the ocean or whatever. Um, Obviously, since it's traveling in a wave, these waves, they have the wavelength, a wavelength. This is determined by how much energy that the photons within the wave contain, and it also determines how we see it. And now there's a very small, on the grand scale of things, there's a very small sliver of wavelengths that we can actually see, and we call this the visible spectrum. Um, we'll get to that in a little bit. I'm not going to go a ton into that, but there are other ranges of energy and wavelengths that we can't necessarily see, but we can detect. In the case of the sun, the energy that the energy at which the photons contain gives them a wavelength that appears as the color yellow or orange, depending on the time of day. And obviously, it's a little more complicated than that. Like, it's bounced around in the atmosphere and whatnot. But what does this lead us to? Can we solve problems with the knowledge that we already have? And we can. So, like, I'm obviously not going to derive the equations, but we have some equations that have already been derived that we already know. You can find these online pretty much anywhere. And this can help us determine the wavelength that these photons travel at and the energy they contain. So on the next slide, we got a couple equations here. Equals HF, that's energy is equal to Planck's constant times the frequency of whatever you're talking about. E equals RH. It's supposed to be R subscript H. That's Reynolds number times 1 Ni squared. N is just an energy level. Not going to get into that. That's quantum numbers. 1 minus 1 divided by NF. That's another quantum number squared, and F is equal to C divided by lambda. F is still frequency, C is the speed of light, which is 3 times 10 to the 8 meters per second, and lambda is the Greek symbol that we use in chemistry and physics for wavelength. Now, here's a little bit of math I have given. This is just one example, and I understand this is probably a little all over the place, but here's that Reynolds equation that we had from before. Energy is equal to Reynolds number times all of that. Reynolds number, put it up there. It's something like I have memorized, but we don't necessarily need to. It's you find it in your chemistry book, your physics books, or it's online if you really need to find it. That's 2.17 times 10 to the negative 18th joules. That's the units in. And Planck's constant, which is the h there, is equal to 6.626 times 10 to the negative 34 joules per second. So in this situation, don't need to get into it, but let's just assume your Ni, which is your initial energy level, is equal to 2. That's your quantum number. It's equal to 2. And Nf, that's a bad F, I understand, is equal to 1. Right? Using this equation, we can just plug in everything we already know. There you go. We get E is equal to negative 1.63425 times 10 to the negative 18th. Now, the reason it came out negative is that E, it's actually the change in energy between energy level 1 and energy level 2. And since we're going from 2 to 1, 2 is going to have a higher energy level, and therefore the change is going to be negative. But let's just ignore that. Let's just say the energy is equal to 1.63425 times 10 to the negative 18th. And I in my work, I have the negative still there, but I erased it when we get to the lambda at the end. So again, a reminder, h is equal to 6.626 e to the negative 34, and we need that for this equation equals hc divided by lambda. And if we remember earlier, E equals hf is another equation we have for energy, h times the frequency, and F is equal to C divided by lambda. So all we did here was the F was replaced with C divided by lambda because F is equal to that. We know C, right? And we're trying to find the wavelength from a particle moving from the n equals 2 to n equals 3 energy levels, or n equals 1 energy level, my mistake. So we know the energy difference is negative 1.63425 times 10 to the negative 18. So we just plug in all the numbers we know. We know Planck's constant, 6.626 times 10 to the negative 34 in joules per second, and 3 times 10 to the 8th in meters per second. That gives us a lambda, if we just solve everything, of 1.216 times 10 to the negative 7 meters, or 121.6 nanometers. Now, remember, the visible light is something I talked about earlier. 121.6 nanometers is not visible light. It's actually just outside of it. It's ultraviolet lights, but ultraviolet rays, which is fine for what we're talking about, which is the sun. Everybody knows UV. You got to put sunscreen on, protect yourself from the UV that the sun emits. I didn't really run the numbers, and I couldn't remember what the jump from 2 to 1 is for the quantum energy states, but it still works, right? Our visible light is generally assumed to be between around 350 all the way up to your 800 sort of range, and you can see what color corresponds with what wavelength based off of this. What entirely all that math meant, I understand I probably didn't explain it very well. I just thought the math would be better to be seen first and then explained. The jump from, we have a particle, let's just say hydrogen. The sun is made mostly of hydrogen and helium. Let's just say hydrogen. Particle of initially at n equals 2 energy level, jumps down to n equals 1 energy level. So the energy change we found from that is negative. It loses this much energy. That energy is going to be released as a photon, which is what we were talking about earlier, right? And so if this is the energy that a photon contains, right? That's from a hydrogen particle losing energy. Then that's where this wavelength is coming from. This is the wavelength of that photon, right? Which is the 121.6 nanometers. And photons, the wavelength at which photons travel, again, determines how we categorize that energy. Or how we categorize it as radiation, sorry. So what can we take away from this? Well, you know, basically the wave particle duality theory, in my opinion, it's really cool, because at one point the Newtonian physics, we thought we knew everything, which is our traditional physics and chemistry. We didn't think we knew everything, but we thought we had a pretty good understanding. And for a while, everything kind of just followed Newtonian physics, and we're like, all right, we get a pretty good understanding. We know this is how it works. But a couple smart guys come in, and they go, that's not entirely how it works. You see light, like it doesn't act entirely that way. And then we started introducing, well, this thing it doesn't have mass, but it has energy, da-da-da. Basically, the world is not, or everything is not as straightforward or obvious as we may think it is. And no matter how much things fall in line, something may come up that we've never seen before, and it throws your entire theory awry. Really, what that says, there's always more to be discovered. We can always understand more. We should never stop trying to find answers and make our world make more sense. The more we make the world make more sense, the more we can create beautiful technologies that we all enjoy.